All right. Hello, class. Um, oh my gosh. Hope you're having a good afternoon. Hope you had a good weekend. Um, my weekend was pretty good. As you may know, I'm trying to get into foraging, and so I have to put together a lot of items, and so I did some of that this weekend. Um, a little bit of sad news: Bug is not feeling very good. I think he has an ear infection, so he's been whining all day today. We got 5 people watching. Hey, Justin. Hey, Rowan. Hey, James. Hey, Alex. And hey, Steven. Oh, someone just dropped out. I wonder who it was. So I have some news items for you that I'm just going to say and say here. Um, so first thing, the quiz this week is there's no additional work for the quiz this week. If you did the daily items last week, all you're going to do is uh, just send me your work and I'm going to check it off. I'm not going to check it for correctness. Um, all I'm going to do is just check it off. You can still work in groups of 4. You're just going to send me your daily items, okay? The other thing I wanted to say is don't overwork yourself, okay? I'm assigning probably more than I should, but I'm not expecting you to complete it all, okay? So just do as much physics as you feel like doing for a given day, and then just stop, okay? If my class is causing you anxiety, then don't worry about it, okay? Just do less physics if that's the case. Next thing I wanted to talk about is I'm going to do another tech check-in because the viewership has declined in all my classes, but I want to see who's actually watching again, and just uh, figure out who's not watching, and so I can figure out what's going on with those people. Okay, so with the news out of the way, let's get into Rowan. If you click, so I've still created a document called quiz, April 27th, and it has all the details in there. So open that document. I believe I want you to title the email CHL_4/27. Okay. All right. So getting to the physics. This is the 2014 electricity and magnetism exam. This is the exam that my brother took when he took AP Physics C. My brother went to the same high school as me. My brother had the same physics teacher as I did. And I think he got a 3 on this. I don't know. I've never asked him. I think if he had gotten a 5, he would have shared it with me. So I know he didn't get a 5, and I think my mom told me that he got a 3, but I don't know for sure. Maybe he didn't pass it. So this is the one my brother took. All right. So it says physics students are analyzing the circuit above. It looks like a simple resistive circuit. A variable DC power supply is connected to an ammeter and 3 resistors. The resistances of the 2 known resistors are 50 ohms, but the resistance of the 3rd resistor is unknown. The students collect data on the potential difference across the power supply and the current measured by the ammeter as follows. Okay. on the grid below, plot the data points for the current as a function of potential difference. Clearly scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. So I'm going to go ahead and do that. I normally wouldn't do a question like this. So potential difference, 2, 4, 6, 8, 10. So here we have 2, 4, 6, 8, 10. Okay? And so I should label that V parentheses V. And then I have current in milliamps. Okay. And I'm going to have this be 50. Okay. So if I plot my points here, I get 40 for a potential difference of 2. I get, for a potential difference of 4, I get like 55. Okay. For a potential difference of 6, I get 97, which is basically 100. For a potential difference of 8, I get 138, which is right around here. And for a potential difference of 10, I get 155, which is like right here. So drawing a line of best fit through the data gives me something like this. Okay. Looks like it goes through the origin. All right. Using the straight line from part A, calculate the total resistance of the 3 resistor combination. So I did part A. So now I got to go to part B. So I can see the slope is roughly, I'm going to say 160 milliamps over 10 volts. So that means 16 milliamps per volt, which is 16 times 10 to the minus 3 amps per volt. Now, we can see I have a graph of I versus V. So if you look at Ohm's law, V equals IR, I can see that it's actually V over I, which is resistance. And my slope is basically I over V, so I need to do the inverse of this to get the resistance. So doing the inverse, 16 times 10 to the minus 3 over, and then I got to do that to the negative 1 power, and I get a total resistance of 62.5 ohms. Okay. Calculate the resistor value of, calculate the value of R1. So I can see if I look at the original circuit, it's basically 100 ohms in parallel with R1, and that equals 62.5. Okay? So that means that 1 over R1 plus 1 over 100 equals 1 over 62.5. okay? So I can take that and I can solve for R1. And that gives about 167 ohms. All right. Part D, it says calculate the resistance, or calculate the current. The power supply is fixed at 12 volts. Calculate the current through R2. So if we look at the circuit, if I apply 12 volts, the total amount of resistance is 62.5, and that's going to allow me to get the current that flows out of the battery, which will be 12 over 62.5 equals 0.192 amps flows out of the battery. Okay. Now, if we look at it, the 100 ohms. So here we have R2 and R3 combined to make 100 ohms. Okay. And then there's the unknown resistor, which we found out was 167 ohms. And this is a 12-volt supply. I didn't need to do this work. I don't know why I did that work. It's easier than that. So I can see that the 12 volt is in parallel with the 100 ohm resistor. So the 100 ohm resistor is going to get 12 volts. So I have V equals I times R. 12 equals I times 100, which means that I equals 0.12 amps. Okay? And because both resistors on the right branch of the circuit are in series, they're both going to get that same current. Okay, moving on to part E. Resistor 3 is now removed and replaced with an open switch in series with a uncharged 4 nanofarad capacitor, as shown below. The power supply is 12 volts. Calculate the current in R2 immediately after the switch is closed. So after, hey Ruby, after the switch is closed, the important thing to know is that if you have an uncharged capacitor provides zero resistance to current flow initially, okay? Once it starts to charge, then it starts to block the current. So if I think about the R2 is basically going to be in a circuit that looks like this. It's going to have no resistance from the capacitor whatsoever. So the current is going to be 12 over 50, which is 0.24 amps. All right. Part 2, a long time after the switch is closed, will the magnitude of the current in R2 be greater than, less than, or equal to the current through R2 found in part D? I would say that it would be less than. In fact, once the capacitor is fully charged, no current is going to flow through the capacitor because, because if current were flowing through the capacitor, the amount of charge would be changing. So the current is going to eventually be completely blocked by the capacitor. So you're gonna go from 0.24 amps to 0 amps. F. The 4 nanofarad capacitor is replaced with an uncharged 10 nanofarad capacitor. Will the magnitude of the current in R2 immediately after the switch is closed be greater than, less than, or equal to the current in part E? It's going to be equal. Why is that? It's because, like I said, an uncharged capacitor is basically like it provides no resistance, regardless of the capacitance. The value of the capacitance is going to change. It's going to change how quickly the capacitor charges up, but it's not going to change that initial current. Okay? So I'm going to move on to the next one. Number 2. That was kind of a weird RC circuit problem because it was like an RC circuit problem that didn't ask about anything involving the actual like charging of the capacitor. That was a weird one. Okay, a rectangular loop of wire is shown on the left in the figure above. Mass M, length L, width L/4, and resistance R. It is initially moving to the right at a constant speed v0 with no net force acting on it. At time 0, the loop enters the region of length 2L that contains a uniform magnetic field B directed into the page. The loop emerges from the field at time t final with speed v final. Express all answers to the following in terms of M, L, R, B, V0, and fundamental constants as appropriate. A. Let X represent the position of the right end of the loop. Place a check mark in the appropriate box in each column to indicate whether the speed of the loop increases, decreases, or stays the same. Okay, so what we can see now, if we think about it, if we think about this one, the loop doesn't want the flux through it to change. Okay, so the forces on the loop are going to be forces that prevent the flux from changing. So as the loop enters the magnetic field, the loop says, no, 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 I don't want the flux. So it's going to try to slow down, okay? Because slowing down is kind of like the best it can do. It would like to push itself out of the magnetic field, but it can't do that. So the speed of the loop in that first part, it's going to slow. So I'm going to actually annotate the document. The speed of the loop is going to decrease. All right. Now, if we look at the second part, when X is between 2L and 3L, the loop is fully in the magnetic field. So the flux isn't changing anymore. So there's no induced EMF in the loop, which means there is no current flowing in the loop, which means there's no magnetic forces on the loop. So once it's fully in the loop, the speed is going to stay the same. Now this region is when it starts to exit the loop, or exit the magnetic field, okay? And again, once the loop is fully in the magnetic field, now what the loop wants is it wants to keep the flux. So there's going to be forces on the loop that try to keep it in the magnetic field. And so it's going to slow down again. And then once it's fully out of the magnetic field, its speed is going to stay the same. All right? So I'm going to say see the board. Ooh, the mail came. I'm going to check and see if I got any packages. bug. All right. That was a little bit scary. I didn't get any packages, but I got a letter from the IRS. So I was like, oh no. But it was just telling me that I got my stimulus check. Okay. So we are on part B. It says derive an expression for the magnitude of the induced current in the loop as it enters, as the right edge enters the field. So flux is NBA cosine theta. Okay. So it's going to be NBA, and it's perpendicular to the loop. So I don't have to worry about the cosine theta term. N is also 1. The area of the loop is going to be length times width. So it's going to be L over 4 times, now this is the area that gets the magnetic field. So I'm just going to leave it as W. Because if we think about it, the only part of the loop is getting the magnetic field. So I'll just call it W, not the entire length L. Now to get the induced EMF, I have to take this flux and divide it by time. So I'm going to get B times L over 4 times W over time. Now W over time is the speed of the loop. So the induced EMF is going to be BLV over 4. And then the induced current is going to be E over R from Ohm's law, which would be BLV over 4R. Boom. Okay. So this is V naught, I think. What is the direction of the induced current in part B? So as it's entering the field, we're creating a flux into the page. So the loop says, no, I don't want flux into the page. So it's going to try to create its own flux out of the page, which would be a counterclockwise current. Okay. D, write but do not solve a differential equation for the speed v of the loop as the loop enters the magnetic field. Okay. I see why my brother flunked this. This 2014 AP Physics exam got really bad scores, and my brother was just like, yeah, the free response was brutal. Okay, so I'm going to use F equals MA. All right. And A is, of course, dV dt. So we have m dV dt. That's what makes it a differential equation. Now the force is the magnetic force. So the force is going to be ILB. Sine theta, but again, the theta term is going to be 0. And actually, the length of wire that is experiencing a magnetic force is going to be only this front edge of the wire. That's the only part that's going to be experiencing a force. So I'm using only that length. Okay. Now the current in the loop, I already solved for. It's this. Okay? It depends on the speed. So what I can do is I can plug that into here. And so what I would get is BL V naught over 4R times L over 4 times B equals M dV dt. And the force is going to slow the thing down so it's in the negative direction. And this is going to be true for any speed that it has, so I can get rid of the V naught. And so I would get minus B squared L squared over 16 Rm times V equals dV dt. That's the differential equation. All right. Laborious. E. What is the direction of the acceleration of the loop just before its left edge leaves the field? Again, it's going to try to stay in the field. So its acceleration is going to be to the left. Okay? All right. Let me see if I have any questions. No, I'm not going to do a mail unboxing stream. I will when I get the forge. All right, question 3. This is the one that stumped my brother. He actually called me afterwards and was like, I don't know what to do. Or he said, can you solve this? I couldn't solve this. So this is CHL 427 part 2. And we're doing question 3. Okay, so a scientist describes an electrically neutral atom with a model that consists of a nucleus that is a point particle with a positive charge Q at the center of the atom and a negative electron volume charge density of the form blah. On the axes below, let R stand for the radius of the Gaussian sphere. Sketch a graph for each of the following charges enclosed by the Gaussian sphere as a function of R. Explicitly label any intercepts, asymptotes, maxima, or minima with numerical values. Okay, so if we were looking at the nuclear charge, a Gaussian surface that encloses the center, all the Gaussian surfaces enclose the center of the atom. Okay, so no matter how big the Gaussian surface is, it's always going to include the nuclear charge. Never more than it, never less than it. So it's just going to be a flat line like that. Okay? As far as the electron charge, what we have to do is remember, the charge enclosed is the integral of rho times 4 pi r squared dr. Okay? Now, rho, it says, is minus beta over r squared times e to the minus r over alpha times 4 pi r squared dr. The r squareds cancel out. Then we have minus 4 pi beta integral from 0 to r of e to the minus r over alpha dr. So doing that integral is going to give 4 pi beta alpha e to the minus r over alpha evaluated from 0 to r So that gives okay. So if you were to graph this, its negative, its value at r equals 0 is 0 because you get 1 minus 1. And its value at r equals alpha is going to be the entire charge. And it's kind of an exponential rise. So it's going to look something like this. Like that. And then it's going to stay constant. Because then we've enclosed the entire electron cloud. All right. B, the dashed curve on the graph below represents the electric field as a function of distance r due to the positive nucleus of the atom without any electrons. The nucleus is modeled as a point particle of charge plus q. On the same graph, sketch the electric field as a function of r for the neutral atom as defined by the scientist's model, which includes the negative electrons surrounding it. So basically, once your Gaussian sphere, once your Gaussian sphere encloses the entire electron cloud, then the charge enclosed is 0, and then you get an electric field equals 0. So the electric field has to go to 0 at the outside edge of the electron cloud. So your electric field is going to look basically the same at first, but then it's going to drop to 0 faster and then boop, hit 0 right there. And then it's going to stay 0. Use Gauss's law to derive an expression for the electric field strength due to the neutral atom for the following positions in terms of all the fundamental constants. For r greater than alpha, I just said that the electric field equals 0 because the charge enclosed is 0. For r less than alpha, then we have the charge enclosed is the positive charge of the positive charge sorry about that. I didn't see the message. So we have the positive charge of the nucleus, and then we have the charge of the electron cloud, which is this. Okay? And then when we think about Gauss's law for a spherically symmetric thing, the left side of Gauss's law is just E times 4 pi r squared. Okay? So all I have to do is divide both sides by 4 pi epsilon naught r squared, and then or 4 pi r squared, and then I can solve for E. So that's going to give Q minus 4 pi beta alpha minus r alpha, all that over 4 pi epsilon naught r squared. That's our electric field. Okay? Based on the model proposed by the scientist, what is the physical meaning of the constant alpha? I would say Well, alpha is where the electron cloud density becomes 0, so I would say it is the radius of the atom. It's the outer edge of the electron cloud. Okay. So I think that's it. Yeah, that was a pretty tough one, but thank you for watching. And I'm going to do, looks like 2 more E&M free response questions, then we're switching over to mechanics. So on Thursday, we'll start doing mechanics. I appreciate you guys watching, and I hope to talk to you on Discord later on today. Have a great one.